Hey stats class, let's quickly go over the chapter 10 spreadsheets. So if you look at what I got here, these are the winners of the Best Actress Award, Best Actress Oscar for a given year. And this is the actor that won the Oscar for Best Actor that same year. So this is their ages. So what we're seeing is the different ages for actresses versus the same year, the same age of an actor. So males, females. And so if you look at what we've got going on here, each point that I hover over, 2741, there's that point. This point is 23 and 56. 23 and 56 would be that point. We don't know what year it is because we're not given the year here. It's just we're plotting age of the female versus age of the male for that same year. And what we hope to see when we do these are called scatter plots. When we do a scatter plot, we hope to see some type of a relationship between the x's and the y's. We'd like to see, as we go left to right, as the x's increase, the y's increase, or the y's decrease. There's being some kind of relationship. And what we're seeing here is there's not really a relationship. So 29, an actress is 29, the actor is 35. All right. Well, this time the actress is 27, the actor is 41. Well, this time the actress is 23 and the actor is 56. So right here we have an actor who's 60 and the actress is 45. The actress is 65 and the actor is 39. The increase in the age of the actress that won does not really explain very well the age of the actor that won. So correlation, what we call the correlation coefficient, tries to quantify that relationship, tries to quantify how well the change in age of one variable, or not age, the change in the value in one variable tends to explain how the other one is going to change. And R is a number that's between -1 and +1. -1 is less than or equal to R, and that's less than or equal to +1. Okay, so that's the range that R falls into. The closer it is to -1, what that means is a line that goes downhill left to right explains it. Explains the data perfectly if R were -1. If R were +1, what that means is a positive sloping line explains the relationship perfectly. So let me give you an example of perfect correlation. So if I just make a data set and the x's, I just do 1, 2, 3, 4, 5, 6, 7, 8. And then for y, I double x. So 2 times 1, 2 times 2, 2 times 3, all the way down. Well now, yeah, a line's going to explain this perfectly because as x got bigger, so did y. And not only did x getting bigger, we can see that y is getting bigger, we can also easily, with this line, come up with exactly what y is going to be. So when r squared is 1, when this number is 1, that means it's a perfect correlation. The correlation between x and y is absolutely perfect. Now I'm going to grab this stuff from here, Control C, and I'm just going to come over to this other sheet. Put in this sheet won't be on yours, but let me move this over so you can actually see it. That says correlation right there. These are going to be 0 because the correlation is 1, and the p-value calls on F11, which is the test statistic. And the test statistic has 1 minus C11 squared. C11 is this number. So 1 minus 1 squared is 0, and we're dividing by the square root of 0, which is 0. So we're dividing by 0. So once that can't be computed, this can't be computed. And what this means is our test statistic is basically infinite. Remember, this is how far away our value is from the expected value. Expected value is definitely not 1. The expected value is 0 here, and we are infinitely far away from 0. So that's what that is, and then this is divided by 0 because it calls on that value. But I wanted you to see that it is a perfect line going through there is what would make R1, and then if you square R, this capital R squared literally is this value squared. So on this one where our correlation was not 1, it was negative 0.24351. If I square that, if I square this number, so square, I get that number that it's giving me right there. So capital R squared literally is this little lowercase r squared. Now, the other thing I wanted you to see is R also, if I made this negative 2, negative 4, all the way down, we get negative 1 for our correlation, which again is a line perfectly describes the trend. Again, R is a measure of how well a line describes the trend. If R is negative, it just means a negative sloping line describes the trend. Okay, and then if you notice, we square R, negative times a negative is a positive, we get a positive 1. R squared will always be between 0 and 1. 0 means a terrible relationship. 1 means a perfect relationship. 1 or negative 1, I should say. All right, let's do that. Let's make it go all crazy. So negative 2, positive 4, negative 6, positive 8. Let's do negative 7, positive 5, negative 10, and positive 8. So let's make this last one. Like, there we go. That's a little better. I'm trying to find any extreme values. Who's this guy? 7, negative 10. Let's make it 7, negative 5. So what I want you to see here is when R is close to 0, and if R is close to 0, R squared is going to be really close to 0. When these numbers are close to 0, what it means is there's just not any relationship at all between X and Y. As X gets bigger, we'd like to see Y do something predictable. Y also gets bigger, or Y gets smaller. But when I went from 1 to 2, X went up by 6. And then when I went from 2 to 3, well, X went down by 10. And then it went up by 14. And then it went down by 15. And then it went up by 12. And then it went down by 10. It's just, there's no predictable relationship between what's happening between X and Y. Or a line can't predict that relationship. So R is a number very close to 0. R squared is also very close to 0. That just means the line isn't predicting this. All right, now what does the p-value mean? Remember, p-value, we see these in hypothesis testing. In correlation, it means how non-zero is our slope. Remember, y equals mx plus b. If m is our slope, the slope of a horizontal line is 0. So if we did a hypothesis test, so technically we are doing a hypothesis test. We're saying the null hypothesis is the slope is 0. All right, and then the alternate hypothesis is the slope is not 0. Basically, that's what we're doing here when we're talking correlation. It's really something called linear regression is when we're technically doing this, but it's very related to this idea. So remember, how did we disprove this? How did we reject this? We reject the null hypothesis if we have evidence that this is the case. How did we get evidence that this is the case? Within our sample, we show that under the assumption that the slope is 0, we are getting a sample that has a slope that is significantly not 0. But with our sample, our slope was, our line was y equals negative 0.0714x plus 0.0714. And so we're looking at this number, mx plus b, m being the slope. The null hypothesis says the slope is 0. All right, that's our slope. The alternate says the slope is not 0. This would need to be significantly not 0 for us to reject that the slope is 0. Well, that's 0.07. That's not even like a tenth. So it's close to being horizontal. This line is close to being horizontal. So we're seeing an absurdly large p-value. Okay, but again, when our r squared was really strong, and I'm going to change this a little bit. I don't want it to be, I want it to actually show up here, so I'm going to make some of these really close. So we're not a perfect, not a perfect line, but it still does a really good job. You know, we just have barely any deviation away from the line. So we're seeing a really strong negative sloping line that describes the data. So if this is really close to -1, really close to -1, r squared is really close to 1. And now we see that p-value has 7 leading zeros. And just like before, what did the p-value mean? It meant that the null hypothesis is probably not right and that the alternate is true. So now, even though we're at -1.96, and maybe that doesn't seem, you know, that far away from 0, statistically speaking, it is very much different from 0, especially with, you know, the amount of data that we have to have a p-value that's strong suggests there is a very strong linear pattern here. And we're predicting that change in the y-coordinates very accurately with this line. All right, and then again, what does this mean? Our line is y equals -1.9606x minus 10, a tenth, 0.1086. What does that mean? Well, since there's such a very strong correlation, if we picked any x that fell in between 1 and 8, like if we picked x, let's say x was 5.75, we would be very confident that the y-coordinate that would go along with that would be -1.9606 times 5.75. That x, whatever, you know, the x is, we multiply it by this number, we subtract this number, and that should be the y that we would see with it. Okay, that's a little bit less than this, and a little bit actually more than this. That's where we're kind of dipping down a little bit right there between those. We're a little bit off, but we would expect that a number, if I'm at 5.75, there's 5, there's 6, so 5.75 is a little closer to 6 than 5. That point on the line, -11.38, that's where we would expect the y-coordinate to fall. All right? So we're a little bit above the actual point here, we're a little bit below the actual point here, so we're coming in a little low even to that actual point. But that's the idea. It's when you have strong correlation, and a good fit linear model, we can use the line to predict values that aren't from the data set. We can predict other values with it. All right, if we want to update this to our project, so I've got the stats project. If we want to update this to our project, I've got one labeled correlation here now. I can take my raw data. So my raw data was the NBA 3-point leader for each season. So technically it looked like this. Let me sort smallest to largest and expand. So this is what, I don't know why that didn't grab that. This is what my data looked like to begin with. Let me go back to the bottom and paste that. I don't know why that didn't go in there nicely. 41, 1028. So in my correlation one, I'm going to highlight all of this. I'm going to go up here to the very top, and I'm going to click on Insert. And then I'm going to select this guy right here, the Insert Scatter. So Insert Scatter, and then I just want that very first one. It's just the dots. Okay, it doesn't have a chart title because I didn't have anything labels for my X's and Y's. So I'm just going to write NBA 3-point leader in attempts. I think it was since 1979, I think, if I remember. So anyway, there's my example data. Okay, I can right click any data point, add the trend line. Okay, when I add the trend line, I also want to add the equation on the chart and display the R squared. Okay, so there is my data. All right, in addition to that, I also want to put in all the correlation stuff from this chapter 10 spreadsheet. So all I'd have to do is grab my chapter 10 spreadsheet, click on the R, drag all the way to the right, the p-value and the test statistic, Control C. All right, come back into my project example, and then Control V. All right, and you do want to make sure when you do this that you put this first cell right up beside your data. So if you put let me just show you what would happen if you pasted it one row off. It updates the values to be, see it says BBCC. And the reason why it's doing that is because in my spreadsheet I'm in row C and it's grabbing stuff in column A and column B. So if I move over, since I'm in C, it's looking to the two beside it. But if I paste it here, right? If I pasted it in row D, the two beside it are BB and CC. Okay, you can paste it wherever you want to. You just have to tell it where your data is. So mine's in A and B. So I could go over there and just say A and BB, and it would fix it and update it. All right, and so once you got that, you got your p-value, you got your test statistic, and you can determine if you have, if you indeed have a correlation between your two variables, whatever you have for X and whatever you have for Y. 0.84, that's a strong positive correlation. Positive means as this gets bigger, this is years since 1979. So for all the years since 1979, this is strongly correlated with the number of three-pointers that the NBA leader for three-pointers that year had. So what does that mean? That means that time passing is a good indicator that three-point attempts are going to increase, and that's happened in the NBA. So that's something I would expect would have a very strong correlation. P-value is 11 leading zeros, so that just indicates that this is 12.858 is very much non-zero. So a line does a great job of predicting this. All right, so you can add this if you choose. I've said it already. I'm not going to count off for your correlation. If you don't want to put correlation on there, you don't have to, since we're out of time. But if you do want to put correlation in there, you're more than welcome to.